Welcome to the next session on virtual labs. In this session, we are taking up experiment number 6 of Machine Dynamics and Mechanical Vibrations Lab. The title of the experiment is Rotating Unbalance. This is a continuation of 4th and the 5th experiment on forced vibration of single degree of freedom system, wherein we are going to study about a rotating unbalance present in a system and how a vibration is induced because of it, and that's what you're measuring using the virtual lab. The aim of the experiment is to observe the effect of damping in forced vibration of single degree of freedom due to rotating of unbalanced force. So there will be some unbalanced force created because of some rotating mass in the system, and that's what we are going to study here. This force will be a type of forced vibration creator because it is a force which is unexpected, not created by us. It will be created because of a particular part which is rotating and causing some force, and it is continuously acting on the system. Let's see the theory of rotating unbalance. Rotating unbalance is the uneven distribution of mass around an axis of rotation. Unbalance is caused when the center of mass, inertia axis, is out of alignment with the center of rotation, geometric axis. As you can see here in the figure, this mass m, which you can see, this should be aligned with the center of the rotation of body, but actually it is off-centric, it is in some other plane, and that's where it is rotating. When an object is forced to spin about a fixed axis, if the mass is not evenly distributed about that fixed axis, then a centrifugal force resulted from this unbalance can induce an exciting force due to which the structure vibrates. So as it is written here, this mass is now going to create a centrifugal force of its own, and this will be a disturbing element for the entire body. So the structure is going to vibrate because of this force. Unbalance in rotating machines is a common source of vibration excitation that one sees in every day, such as vibration of automobile engine or the washing machine. So this is very common if something is not moving about a particular axis, but it is moving about some other axis which is unexpected and eccentric to the geometric axis of the body, then obviously you will see that there is some unbalanced force which will cause vibration. One might have experienced the effect of vibration due to rotating unbalance while driven a car where the wheels are not balanced. This is something which you may have experienced in your life if you have driven a car and if you have felt that the wheels are not balanced properly, then you will feel that as if your mass of the car and the wheels are off center and it is just shaking. At some particular speed, the car will shake, sometimes quite violently. At this speed, the rotational speed of the wheels is such as to be close to the natural frequency of the car on its suspension, so that the amplitude becomes a maximum. So when the rotational speed of the wheels is such that it is equal to the natural frequency of the car suspension, then what can happen is the car can start shaking very violently. That is, resonance occurs. This phenomena is really important because if not dealt with promptly, one could have catastrophic failure due to the fatigue caused by the vibration. So because of fatigue failure, the car can completely go into a different uncontrolled mode and it can cause catastrophic failure. To study the effect of vibration due to rotating unbalance, an unbalanced rotating machine model as single degree spring mass damper shown in figure having an equivalent unbalanced mass m rotating at frequency omega with its CG at a distance e from the axis of rotation. You can see that a car or a washing machine which is undergoing such a kind of violent motion has now been modeled in a simple way in the form of spring damper, and this is that mass which is disturbing the entire system. So it is marked eccentric at a distance e from the geometric axis of the body. This results in a centrifugal force proportional to the square of frequency of rotation. The centrifugal force is the maximum value of sinusoidal excitation in any direction. So we will see the equation of motion in the vertical direction can be written as mx double dot plus cx dot plus kx is equal to me omega square sine omega t. The small m is here the mass which is unbalanced and it is causing the vibration. This capital M is the mass of the entire body and not of the disturbing element. C is the damping coefficient, we know it. K is the stiffness. You can see here the spring has been modeled here. So K is the stiffness of these springs. E over here is the eccentric distance at which this mass is causing the centrifugal force. Omega is the angular velocity with which it is moving. Sine omega t. So you can see here there is a sine input of the disturbing element in the system. Steady state amplitude x and phase angle due to vibration caused by the rotating unbalance is given by these two equations. So if you want to calculate what is the amplitude and what is the phase angle, you can use these two formula. What we are doing over here in the experiment is a simulation. That is at the back end, these formulas have already been added and the calculation is shown on the screen. So you can also use these formulas and check the values. And equation 2-3 written in dimensionless form as, now this equation, if you want to write this in a dimensionless form, which means the total term will have no unit of its own, but each individual quantity over here definitely has its own unit. For example, x is the amplitude, small m is the mass, eccentricity is a distance, so it could be something like in meter, amplitude also is in meter, mass capital M is also kg. So total no unit is there on the left hand side. When you see the right hand side, omega and omega n has a unit of radians per second, which means overall no unit, and zeta has no unit of its own. So the left hand side and the right hand side gives out no unit, which means they are the dimensionless form of the same equation. When you see the equation number 5, this is also the dimensionless form of the third equation. Here also a small modification has been made such that there is no unit left on the right hand side and the left hand side. Next is the procedure. We are going to follow the same procedure that we have done for experiment number 4 and 5. So I'm not repeating it here. I'll directly take you to the simulation tab and explain over there itself. This is the self-evaluation tab. You can just solve these questions and check out your knowledge. This is the simulation tab. First, we will change the stiffness to a particular value and we will also change the mass. If you change the mass and the stiffness, you can see here omega n changes. Otherwise, omega n is not affected by any other value. We can change the unbalanced mass, as you can see, which is rotating. Let me set this value to 8.5 kg meter. And the rotating speed of the mass, I can change it to 9 radians per second. I'm just increasing the speed. Now what we will do is, these values will remain constant. We will only be changing the value of damping ratio. First, we will take the value of damping ratio as 0.19 and we will see what is the graph of magnification factor versus frequency ratio and phase angle versus frequency ratio. So this is the first graph obtained. Next, we will change the value of damping ratio to be more than 0.35, but it should be less than 0.707. And we will see the graph for the second reading. Again, we will change the damping ratio more than 0.707. So we have taken as 0.89 and we will see the graph for this reading. So this is how the graphs can be plotted by varying the damping ratio. This is the simulation tab that we have just discussed. Next, we have the assignment tab where a question is given. You can try solving it. Next is the section for quiz. There are a few questions given. You can try solving them. Next is a video section given where the explanation of this simulation part is given. References are given for the preparation of the theory and the simulation one. So these are the books referred. And finally is a section for feedback. You can give your valuable feedback after performing the experiment. So with this, I end the session. I hope you have understood how to analyze a rotating unbalance for forced vibration, single degree of freedom system using virtual labs. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.